Good morning, dear students. Today we are going to discuss the basic concepts of quantum mechanics. Okay. We are going to discuss the formal structure of quantum mechanics as a set of 5 postulates. Mainly today's concept is focused on postulates of quantum mechanics, in which we are going to discuss the general properties of operators, eigenvalues, eigenfunctions, expectation values of observables, orthogonal and normalization conditions, and also time development of a quantum system. Okay. Now, the postulates of quantum mechanics. In the postulates, we have 5 postulates mainly. The first postulate concentrates on the state of a quantum system, and the second one deals with the operators associated with various observables, and third one is the eigenvalues. We are going to discuss about eigenvalue equation, where we are going to explain about eigenfunctions and eigenvalues. Next comes expectation value, that will be given in as postulate 4, and next one is the time development of a quantum system. Now let us discuss about the postulate 1. What the postulate 1 states is that it concerns with the state of a system. So what the postulate states is that the state of a system is described by a wave function psi of r comma t. For a single particle, the wave function is a complex function of space and time, that is r and t. This gives the complete knowledge of the behavior of the particle. Similarly, psi of r, which is independent of time, gives the stationary state. Since there is no movement, it represents a stationary state. The use of this psi, we can also find out the probability of finding the particle in the space within r and r plus dr, that is psi star psi d tau. Here it must be focused that the wave function must be well behaved. Well behaved means it must be single value, continuous and finite everywhere. Next comes postulate 2, which concerns with the operators. So according to postulate 2, every physical observable is associated with a linear Hermitian operator. Now the result of all the measurements is a number. The eigenvalue of Hermitian operators are real. Now let us have a table which will show the operators associated with various physical observables. You can see in the table, in the first column we have various quantities, physical observables, and in the next column we have the operators associated with the physical observable. The first one is the position, given by x, and the corresponding operator is x. For the linear momentum p, we have the corresponding operator minus i h cross dou by dou x. Instead of dou by dou x, we can put this dou by dou x is for the single dimensional. If you take for 3 dimensional, we can give it as minus i h cross del. Similarly, for angular momentum, the formula is r cross p. Here we can substitute p, the operator p from the previous column, that is minus i h cross r cross del. Similarly, kinetic energy is given by p squared by 2m, where p is the momentum. We can substitute the operator concerned with momentum here. Therefore, the kinetic energy operator is h cross squared by 2m dou squared by dou x squared, or minus h cross squared del squared divided by 2m. Next, the energy, that is total energy operator, E is given by I h cross dou by dou t. E is the energy and associated operator is I h cross dou by dou t. Now the total energy H, that is Hamiltonian, which is the sum of the potential and kinetic energy, is given by, for kinetic energy we can substitute h cross squared by 2m dou squared by dou x squared, and for potential energy it is V of x. Therefore, the total Hamiltonian is given by h cross squared by 2m dou squared by dou x squared plus V of x, or For the three-dimensional case, we can give as minus h cross squared del squared divided by 2m plus v of x. Next, third postulate gives eigenvalues. The only possible values which a measurement of the observable can yield are the eigenvalues. The eigenvalue equation is given by A psi n equal to A n psi n. The eigenfunction psi n form a complete set of independent functions. The eigenvalues A n are just numbers and the capital A is the operator associated. Now let us find out the eigenvalue for any function. Here the function is given as psi equal to e power 2x and the corresponding operator is d squared by dx squared. Let us substitute in the above equation. Instead of a we can substitute d squared by dx squared, and the given function is, instead of psi n we can substitute e power 2x, and if you differentiate twice you will get 4 into e power 2x. We can see that the e power x is there on both the sides and d squared by dx squared is the operator, and the eigenvalue instead of a in the above expression we have 4 here. Therefore, the eigenvalue of the eigenfunction psi equal to e power 2x is 4. Next, postulate 4, which gives the expectation values. The average value of an observable corresponding to the operator observable A corresponding to the operator alpha for a system is described by the wave function psi as given by the expectation value of A equal to integral psi star alpha psi d tau divided by psi star psi d tau. Here the quantity A in the left hand side is the expectation value. If the wave function is normalized, then the denominator becomes unity, that is integral psi star psi d tau equal to 1. Hence, the expectation value of A becomes A equal to psi star alpha psi d tau. Now, the previous 4 postulates which we dealt so far concern with the properties of the quantum system at any given instant of time. Next, let us discuss about postulate 5, which gives the time development of a quantum system. The development in time of the wave function is given by the equation h psi equal to I h cross dou psi by dou t. Here, this is nothing but h psi equal to E psi, which represents the time dependent Schrodinger equation. Here h is the Hamiltonian operator and I h cross dou by dou t is the operator associated with energy. If the wave function is known at some initial time, the above equation determines psi at any other time. So, this is about the postulates, 4 postulates. I will summarize the 4 postulates once again. So, postulate 1 concerned with the eigenfunction, okay, which gives the state of a system which is described by a wave function. Next, postulate 2, which concerned with the operator. It states that every physical observable is associated with a linear Hermitian operator. And the third, postulate 3, eigenvalues. So, which states that the only possible values which a measurement of the observable can yield are the eigenvalues. And next, expectation. The postulate 4 concerned with the expectation values. It states that the average value of an observable A corresponding to the operator alpha for a system is described by the wave function psi is given by A equal to psi star alpha psi d tau divided by psi star psi d tau. And the next one concerned with the time. How time reacts with time associated with a quantum system. So, it gives the time development of a quantum system. It states that the development in time of the wave function is given by h psi equal to I h cross dou psi by dou t. This is nothing but the time dependent Schrodinger wave equation. Next, here we will concentrate only on the expectation values of dynamical quantities. How we can calculate the expectation values of dynamical quantities, what we mean by expectation value, and then we will also calculate the expectation values for various observables also. Okay. Let me introduce what we mean by an expectation value and what is the necessity for an expectation value. According to Bond, the wave function psi has probabilistic interpretation. Therefore, it is essential to calculate the average or expectation values of any dynamical quantity defined by the wave function. In physics, such dynamical quantities are space coordinates, momenta, and energy of the system. The average or expectation value of a dynamical quantity is the mathematical expectation for the result of a single measurement, or it may be defined as the average of the result of large number of measurements on independent systems. Now let us calculate the expectation values of various physical observables. Let us take first how for any operator, how we can calculate the expectation value. By definition, the expectation value for any observable f for normalized wave function may be written as f equal to p of r comma t f operator d tau, where p of r comma t is the probability of finding the particle at any instant of time in space, which is given by psi star psi. So instead of p of r comma t, let us substitute psi star r comma t into psi of r comma t. Therefore, this equation becomes psi star r comma t f operator psi of r comma t d tau. Now, the expectation value of position operator is given by psi star r comma t or psi of r comma t. This is the three-dimensional case. If we have for a single dimension, for if you calculate for the x direction, then the expectation value of x will be equal to psi star xi d tau. For y, psi star y psi d tau. For z, psi star z psi d tau. Here the left hand side x, y, z are the expectation value of the coordinates x, y and z of the particle respectively. Similarly, for the potential energy, the expectation value will be given as V equal to integral psi star r comma t V of r comma t psi of r comma t d tau. Next, let us calculate the expectation value of energy, which is given by E equal to psi star E operator psi d tau. Let us substitute for E the operator concerned, which is given by I h cross dou psi by dou t. Therefore, this equation becomes I h cross integral psi star dou psi by dou t into d tau. Similarly, for momentum, P equal to integral psi star P operator psi d tau. Let us substitute the P operator as minus I h cross del. Then this expression becomes, since I h cross is constant, let us take it outside the integral. So minus I h cross integral psi star P psi d tau. Now for the x coordinate of momentum, we have Px equal to minus I h cross integral psi star dou psi by dou x d tau, and for Py minus I h cross integral psi star dou psi by dou y d tau, and for Pz also minus I h cross psi star dou psi by dou z d tau. Here the left hand side Px, Py, Pz are the expectation values of the components of momentum along the three directions x, y and z respectively. It is noted that the above formula of expectation values only hold if the wave function xi is formally normalized, properly normalized. Then only we have the denominators as unity, otherwise we will have value for denominator also. Okay. Now let us, so far we have discussed about the expectation values of various physical observables and how we can calculate for expectation values. For example, let us calculate for a given function psi of x equal to 2 by L sin pi x by L, which is defined in the regions x lying between 0 and 1. Here it is asked to calculate p and p squared, that is momentum and the square of the momentum, using the above formula. Okay. The expectation value of the observable p in the state xi is given by p equal to psi star p psi dx, where p is the operator associated with the observable P. The operator associated with x component of momentum is P equal to h cross by I dou by dou x. So let us substitute this value in the above expression. Then we will get psi star h cross by I dou psi by dou x into dx. Here instead of psi, we can substitute the given function 2 by L into sin pi x by L for in the interval 0 to 1. After substitution, we get this integral 2 by L sin pi x by L into the component of momentum h cross by dou by dou x, again the same wave function, given wave function. When you integrate, you will get, if you take the constants outside, 2 by L is a constant, h cross by I is a constant, pi by L is also a constant. What to be integrated then? Integral sin pi x by L cos pi x by L dx. Let us integrate in the limit 0 to L. When you integrate, we will get cos 2 pi x by L divided by 2 pi by L. Let us give the limits as 0 and 1. If you substitute, we will get cos 2 pi minus cos 0. Therefore, you will get, for both the quantity, you will get 0. So, P equal to 0. Therefore, the expectation value of the momentum is 0. In the similar way, we can calculate for P squared also. Instead of P, let us substitute the square of the given function, and finally we can integrate as usual. Then we get, so P squared equal to, finally we get pi squared h cross squared by L squared, and if you give sin 2 pi minus sin 0, therefore that becomes 0, second quantity inside the bracket is 0, so therefore you get L alone, L cube and L cancel out, and we get in the denominator L squared. Therefore finally the expectation value of P squared equal to pi squared h cross squared by L squared. Students, I think that you can clearly understand how we can calculate the expectation value of P and P squared for a given function. Similarly, here it is given another function. Instead of that function, here we have n into e squared minus x squared by 2a squared plus ikx. So the similar procedure has to be followed. Here they have asked, instead of P and P squared, here it is position is asked. Therefore we have substituted x alone. Therefore the given function is integrated and you will get now finally 0. So the expectation value of position is 0 according to this expression. Next one is, it is asked to establish the relation. This is nothing but the commutation relation between Px and x. So Pxx minus xpx equal to h cross by I. We are going to establish this relation. So it is given as expectation value. So Pxx, let us find out the expectation value of Pxx, Px into x first. So instead of that operator in the expectation value expression, let us substitute Psx. For P also we can substitute the operator associated, that is h cross by I dou by dou x. So if you differentiate dou by dou x, we will get x into dou psi by dou x plus dou x by dou x into psi. So dou x by dou x is 1. Therefore for the second term you have only psi. Okay. Next, let us separate the two integrals and we can integrate. So you will be getting, similarly let us have for xpx. So previously we have calculated for pxx. Now let us calculate for xpx. So you get h cross by I integral minus infinity to plus infinity x psi star dou psi by dou x into dx. So previously we have calculated for pxx as xi plus dou psi by dou x dx plus 1. Therefore, if you subtract one from the other, we will get pxx minus xpx equal to h cross by I. So this is the relation which we want to prove. That's all. So let us discuss about the other topics in our next class, girls.